But when you're working with problems in physics, I strongly recommend you keep everything in an algebraic form for as long as possible. Only plug in numbers as the last step of the calculation, okay? You'll find that makes things much easier to follow. In particular, it'll be much easier to track if you've screwed up somewhere. So keep things algebraic for as long as possible. Okay, so you may need to look for implied data. There aren't many examples of this. Classic one is at some point an object is at rest. That means v equals 0. Okay? So you're going to get in the habit of parsing the language of these problems kind of in detail. That's what I mean by implied data. Not a bad idea to draw setup. I'm a big fan of drawing problems before you solve them in physics. And okay, one-dimensional motion, things are pretty straightforward, so maybe you don't need to. Up to you, but I would encourage it. It kind of helps clarify things. And you might, along the way, you might write down key variables, pieces of information that you've extracted from the setup of a problem. You're told that the acceleration is constant and it's 4 meters per second squared. Just write it down on the side of your page so you kind of have that as a reference. And then this last bit is kind of obvious, but okay. So look for, okay, how am I going to write this? The most efficient, okay, this isn't the right way of writing this sentence, but I'm going to continue anyway. What I mean is look for the equation that gets you to the answer most efficiently. So look for the most efficient equation that contains your knowns plus one unknown, which is of course the thing you're trying to find, and then simply work with it, okay? So it seems pretty straightforward. It seems like a pretty obvious set of menu items to follow with your problem-solving strategy, and I think you'll find it's pretty straightforward. But we'll be exercising you in a whole bunch of different sort of cases for this. So I'm going to jump in right off the bat now, write a problem, which I suspect may at some point come from your textbook, but I don't remember. I'm going to have you guys work with your partners for a couple of minutes, and then we're going to talk about it and wrap up on this problem by the end of class. Okay, so always a pain writing these things up. I should probably just display them on the screen to save time. So a spaceship is moving with velocity of plus 3,250 meters per second. Its retro rocket is fired and slows the spaceship with an acceleration of magnitude 10 meters per second squared. What is the velocity? Is the question. What is the velocity when the displacement is plus 215 kilometers relative to the point where the rocket was fired? Okay, that is the question. I'm not going to give you guys any other information. Just going to read it again, make sure you've got all of the information. The spaceship is moving with velocity plus 3,250 meters per second. Its retro rocket is fired and slows the spaceship with an acceleration of magnitude 10 meters per second squared. What is the velocity when the displacement is plus 215 kilometers relative to that initial point? Okay, find a friend or at most two. Talk about how you're going to solve it. As usual when I do this in class, I'm not going to get right to the end of the full calculation. That's not the point. The point is for you guys to figure out amongst yourselves how you're going to solve this. Have the framework set up so that eventually you can plug in numbers and get answers. Okay? All right, go for it. I'm going to stop you in about 4 minutes.
Yeah.
Make friends with your neighbors. If you don't have a neighbor, find one. It either means getting up out of your seat.
Okay, keep going. Still have 50 seconds. Okay, so I'm just going to quickly outline what I might have done in terms of coordinate systems in Sketch, and then I'm going to ask you guys to tell me how you solved it. So we talked about one-dimensional motion. I'm going to set this up with this why not, along the x direction. So here's an x-axis, my initial position, x0 here. I've got an initial velocity, which I'm defining in the plus x direction. So I'm going to define this as plus 3,250 meters per second. We're going to be asked to figure out when the displacement is a certain value with respect to the initial value. So there's a displacement, and we are specifically told that this is plus 215 kilometers. Note there's a unit difference here, which we're going to have to worry about. And then we're told that the acceleration is such that, well, we're told its magnitude is 10 meters per second squared. All importantly, what is the direction or sign of the acceleration? It's in the opposite direction to the initial velocity. That is essential information. It is slowing it down, at least to begin with. So that's pretty much all the information I can glean from this. So a quick summary of information that I've passed from the problem, quick sketch, how do I solve it? Okay, so the response was looking over in my menu of possibly 5 equations of motion under constant acceleration, passing a little bit what we said here. Look for the one that contains the known quantities plus the unknown quantity. What is the unknown quantity? What is the velocity at some certain point later on? So we know v0, we know a, we know x minus x0, we don't know v. A quick scan through these 5 equations will draw your attention to this one. Hopefully, we know everything on the right-hand side, so we can plug and chug. I'm not going to put the numbers in, but I'm going to tell you at the end of this that you will end up with the following: v squared. You put in the numbers, you do the appropriate unit conversions. You'll find that this is approximately 6.3 times 10 to the 6 meters squared per second squared. It's velocity squared, so those are the units. The question is, if that's v squared, what is v? Okay. Okay, I heard somebody at the front say something important. Yes. It can indeed be plus or minus the square root of this. Okay, I don't know numerically what this is. It's about 2.5 times 10 to the 3 meters per second, something like this. But it can be plus or minus. This is a point where I want you to stop, having gone through all of the stuff on here and already got an answer. But I want you to stop now and ask the question, does it make sense? Does it make sense that I get 2 answers here, one of which is a positive velocity, another of which is a negative velocity? Yes?
You know that the rock is accelerating, so you use the sign of action of the velocity. The sign of velocity has to be opposite of the sign of acceleration, so you can get your own answers.
Maybe. Let's hear what other people have to say. Interesting. So I obviously purposely chose this problem for a reason, because in some cases you could think about what's going on, and you might be able to exclude one answer as being, as we often say, sweeping things under the rug, unphysical. But in other cases, the 2 answers in this case may both actually tell us something that's really happening about this situation. And it turns out it's the latter in this case, because what's happening, exactly as you described, is that this thing is being accelerated to the left. But it turns out, if you use both of these answers and figure out what time they happen, which of course you can easily do, it's indeed true that it passes this point once when it's still got a positive velocity, but it's still being accelerated in that direction. So in fact, at some instant, it will, for that instant, be at rest, and then it's being accelerated still this direction. So now it's got a velocity in the leftward direction that's continually increasing in terms of its magnitude. So indeed, it passes this point twice. The First time with a positive velocity, which is the positive root of this, and the second time with a negative velocity, which is the negative root of this. Questions?
Does the slows imply that the velocity always has to be in the opposite direction?
No, only initial, right? You might be paying attention that I said the acceleration is in the opposite direction to the initial velocity. Because once it's turned around, the acceleration is in the same direction as the velocity. So keep that in mind, it's super important. So this problem was well chosen because it illustrates some of the subtleties you guys are going to confront when you have to deal with problems like this. Okay, we're out of time, so I'm going to take any additional questions offline. Come on down. Don't forget all the announcements at the start of the
How many? How was summer?
It was good.
Good.